Hello friends, imagine if someone were to tell you that the world and the universe, as you perceive them, are not what they seem. The entities that appear solid are, in fact, composed of empty space, and the events that seem certain may merely be possibilities. This notion might seem peculiar at first, yet it encapsulates the essence of quantum theory, a domain where the established rules of science, logic, and our understanding are fundamentally challenged. This narrative chronicles the scientific revolution that transformed our comprehension of the universe. There was a time when science adhered to straightforward principles. Every action had a specific reaction. However, a pivotal moment arose when scientists discovered that the inner workings of atoms did not align with surface appearances. This marked the beginning of humanity's most revolutionary journey, the journey into quantum mechanics. You are listening to The Book Holder. Today, we will discuss the book on quantum theory, inspired by the contributions of Max Planck and Niels Bohr. We have all learned Newton's laws in school, which state that objects fall due to gravity and that a ball rebounds from a wall due to defined principles. This perspective, known as classical physics, sought to explain phenomena in a clear and linear manner. Scientists of that era believed they had comprehensively understood the universe, with only minor questions remaining. Questions they thought would soon be resolved. However, this notion of scientific completeness was short-lived. A seemingly minor issue, known as black body radiation, shook the foundations of scientific thought. A black body can be understood as an ideal entity that absorbs all energy incident upon it and subsequently emits that energy as a specific type of radiation. When scientists heated such a body and measured the emitted light, they expected classical formulas to yield straightforward explanations. Instead, the resulting graph contradicted their expectations. Classical formulas suggested that as temperature increased, the energy output would also rise continuously, eventually reaching infinite energy at short wavelengths and high frequencies. This absurd conclusion led scientists to humorously label it the ultraviolet catastrophe. This moment was akin to believing one has complete control over a situation, only to be confronted with a reality check indicating overconfidence. Classical physics found itself at a juncture where it had no answers. Newton's laws, which successfully explained phenomena from the heavens to the earth, faltered at the atomic level. Many prominent scientists attempted to resolve the black body problem within the confines of existing theories. Some connected it to thermodynamics, others to electromagnetism, yet all efforts yielded incomplete explanations. It became evident that progress would require a new perspective, one that did not entirely dismiss the old rules but could offer novel insights where those rules failed. Traditional physics posited that nature operated continuously. Now, the question arose, what if nature functioned in discrete units? Embracing this idea necessitated a departure from long-held beliefs, akin to a person coming to terms with a world that differs from what they were taught in childhood. Such a shift often brings profound change, not only in knowledge but also in life itself. This moment marked the inception of quantum physics, as classical physics acknowledged its limitations. Amidst the collective uncertainty surrounding the resolution of black body radiation, one individual dared to think differently. He postulated that perhaps the flaw lay in the conventional approach to thinking. Historically, energy had been viewed as a continuous flow, akin to a river. However, he suggested that energy might also manifest in discrete packets, much like droplets of water. This revolutionary idea proposed that energy is not continuous but rather exists in quantum packets. This notion was akin to asserting that sunlight is not a steady stream but rather a series of individual energy quanta, continuously emitted. However, the conversation was not merely theoretical. It required a formula to substantiate this claim. This led to the formulation of a simple yet transformative equation, E equals h nu. In this equation, E represents energy, h denotes Planck's constant, and nu signifies the frequency of light vibrations. The brilliance of this formula lay in its ability to accurately resolve the black body radiation problem. The graph, once misaligned, now fit perfectly. Where classical physics faltered, this new perspective triumphed. Intriguingly, the individual who proposed this idea did not fully comprehend its implications at the time. He viewed it as a mathematical trick, an ephemeral solution that might not reflect reality. Yet, over time, it became evident that this was not merely a clever ruse but rather a true representation of nature. Consider the implications of having lived your entire life believing that sunlight disperses uniformly, only to be informed that it consists of discrete energy photons, akin to invisible projectiles falling upon you. This revelation may seem strange, yet it accurately reflects the workings of the universe. When an object is heated, it releases energy in the form of these small packets, which subsequently manifest as light, heat, and various forms of radiation. This paradigm shift not only addressed a scientific dilemma but also demonstrated that our reality is far from what it appears. While larger objects may seem smooth and continuous, at the microscopic level, everything is quantized and fragmented. This marked the beginning of a new era in science, equipping it with a new lens through which to view the universe, one that emphasizes understanding possibilities over certainties and embracing discreteness over continuity. Perhaps this was the most crucial turning point when science first acknowledged that its own assumptions might be flawed. Accepting this fact is a profound form of wisdom, whether within science or life itself. With the realization that energy comprises discrete packets, the next pressing question arose: do atomic structures adhere to the same principles? This contemplation led to the emergence of a young mind who provided a fresh perspective on atoms, one that was not only comprehensible but also resolved long-standing confusions. At this juncture, Rutherford had presented a model wherein electrons orbit the nucleus much like planets around the Sun. However, a significant issue persisted: if electrons continually orbited the nucleus, why did they not lose energy and spiral inward, as classical physics would predict? This conundrum troubled many. A novel proposition emerged: what if electrons did not exist everywhere simultaneously? What if they occupied only specific energy levels and transitioned between them? This model suggested that electrons do not travel in continuous spirals but reside in defined orbitals, akin to trains stopping only at designated stations. When electrons transition from one orbital to another, they either absorb or emit energy. For instance, when an electron moves from a lower orbital to a higher one, it requires additional energy, absorbing a photon. Conversely, when descending, it emits a photon. This process accounts for the emission of light and elucidates why even simple gases like hydrogen exhibit intricate spectral lines. The remarkable aspect of this model was its direct application of Planck's quantum ideas to atomic behavior. Thus, the discussion extended beyond energy to encompass matter itself, which also adhered to quantum principles. Previously, scientists believed electrons could occupy any position. Now, it was accepted that they could only exist at discrete levels. This represented a significant shift in understanding, akin to being told one can ascend stairs but cannot pause mid-step. This model not only facilitated comprehension of atomic physics but also illuminated the realms of chemistry, light emission, and spectroscopy. The logic underlying the periodic table became clearer, explaining why each element possesses a distinct identity. This shift cultivated a new generation of scientists for whom atoms transformed from mere spheres into complex playgrounds of energy levels and probabilities. The overarching message of this new understanding posited that the behavior of any entity is contingent upon its internal structure. Often, what appears simple on the surface conceals intricate rules operating beyond our perception, which can be game changers. As scientists delved deeper into the implications of energy existing in discrete packets and electrons residing at select energy levels, they began to explore the intricacies of the microscopic world. This exploration unveiled fundamental principles that fundamentally challenged the foundations of classical physics. The first and foremost principle asserted that energy and matter are quantized. This means that just as one ascends stairs step by step, energy is also encountered level by level. It is not a continuous flow as observed in our daily experiences. Rather, entities, be they light or particles, exist only at specific energy values. The second significant principle was the wave-particle duality of reality. Previously, light was considered purely a wave, yet experiments revealed that it sometimes behaved as a particle. This duality also applied to electrons, which, while being particles, exhibited wave-like properties. Nature, it appeared, played a dual game, sometimes manifesting as a wave and at other times as a particle. This revelation challenges our understanding, as we typically categorize things as either this or that. The third principle introduced was the uncertainty principle, which states that one cannot simultaneously know the exact position and momentum of a particle. The more precisely you measure one, the less accurately you can know the other. This is not merely a limitation of measurement but rather a fundamental rule of nature, suggesting that the universe does not operate with complete certainty. Consider a world in which you can never predict anything with absolute certainty, where you only understand the likelihood of events occurring. This encapsulates the most mind-bending aspect of the quantum world. It is built on possibilities rather than solid certainties. Another intriguing principle is superposition, which posits that a particle can exist in multiple states simultaneously until observed. For instance, an electron can occupy two positions at once, but upon measurement, it resolves into one position. This is akin to a person contemplating two options, ultimately choosing just one when a decision is required. Connected to this is the observation effect, wherein quantum theory asserts that until an object is observed, it exists in an uncertain state. However, once observed, it decides what form it will take. In this context, the observer becomes part of the system, influencing it rather than merely witnessing it. Subsequently, we encounter entanglement, a principle stating that once two particles become entangled, their states remain interconnected regardless of the distance that separates them. This suggests that at the quantum level, our conventional definitions of distance and time become irrelevant. Collectively, these principles illustrate a reality vastly different from our conventional understanding, one where precision is elusive, where the real action lies between maybes, and where the observer influences the narrative of the universe. This is the beauty of quantum physics. Where classical physics delineates boundaries, quantum physics teaches us that possibilities are infinite, and understanding these possibilities may prove more crucial than certainty, even in life. Initially, when the idea emerged that energy and matter are composed of discrete units, many dismissed it as a mere theory with little relevance to everyday life. However, few could foresee that this very theory would revolutionize technology, healthcare, and our understanding in the years to come. The technologies that envelop us today, smartphones, the internet, computers, and lasers, are fundamentally rooted in quantum theory. For instance, semiconductors, the tiny components enabling your phones and laptops to function, are devices based on quantum principles that control the behavior of electrons to transmit data through circuits. Similarly, lasers, which are essential in everything from barcode scanners to eye surgeries and fiber optic internet, operate on the principle of electrons jumping between energy levels and emitting light at specific frequencies. This serves as a practical application of quantum theory. Moreover, magnetic resonance imaging (MRI) has revolutionized the medical field by capturing internal images without invasive procedures. This technology relies on how atomic particles behave within a magnetic field and how their spins respond. Beyond technological advancements, quantum theory has also deepened scientific inquiry. Previously, science operated on predictability. Now, it embraces the realm of possibilities. This shift has expanded science beyond machinery to grapple with questions of life and existence. It raises profound inquiries regarding whether our thoughts and observations can influence the universe or whether two individuals can be connected at a deep level, much like entangled quantum particles. These questions have not only perplexed scientists but also philosophers and thinkers alike. In summary, quantum theory has emerged as a framework attempting to elucidate the invisible world while simultaneously reshaping our reality. What was once deemed an eccentric or radical theory now silently operates within every facet of our lives, exemplifying the true power of science, transforming the impossible into the possible. When quantum theory was initially introduced, it transcended the confines of scientific discourse, compelling humanity to confront profound questions about existence. This was no ordinary theory. It represented a paradigm shift, revealing that our understanding of the universe is far more mysterious and uncertain than we had assumed. The significant realization was that nothing in the universe is guaranteed until observed, implying that entities can exist in multiple states simultaneously. This notion suggests that our perception and consciousness do not merely observe the universe but actively shape it. This insight is so profound that it dissolves the boundaries between science and philosophy. Quantum theory prompts the question: are we mere spectators of the universe, or are we integral to its fabric? Does our existence itself define the universe's form? Another pivotal aspect is the notion of probability. Classical science asserted that with complete information, one could predict future events with certainty. Conversely, quantum theory posits that this is impossible. We can only ascertain the likelihood of occurrences, not certainties. While this may seem a minor distinction, its implications are profound, teaching us that despite our meticulous planning, we cannot control every outcome. Often, we can only navigate based on the probabilities of events unfolding. Furthermore, quantum theory introduces the concept of connectedness. When two particles become entangled, their states remain instantaneously intertwined, irrespective of distance. This principle extends beyond physical particles, hinting at potential emotional and mental connections between individuals. Many philosophers and scientists have pondered whether our thoughts, emotions, and consciousness might also be interconnected at a quantum level, raising the possibility that the universe is not merely a machine but a conscious system. Quantum theory reminds us that reality is not a fixed and definitive entity. It is shaped by our perception, understanding, and experiences. What one person perceives as truth might be seen as mere possibility by another, with both perspectives potentially valid. Ultimately, quantum theory teaches us that the world is not as straightforward as it appears. Every situation can manifest in multiple forms, and each individual's perspective plays a role in unraveling this complex puzzle. Perhaps the most beautiful aspect of this theory is that it offers not just an understanding of atoms and photons but also a pathway toward self-discovery. When science begins to introspect, it transcends its mere identity as a discipline and transforms into a form of wisdom. Reflecting on this journey reveals that the exploration of science has been more than a mere recounting of theories. It is a tale of two individuals' intellect, courage, and perseverance, those who dared to understand the universe at a level that eluded others. They confronted questions that had long been avoided, enabling us to glimpse the invisible world that underpins our reality. Although their thoughts diverged, their shared goal was to uncover the true laws of nature. One highlighted that energy is not a continuous flow but rather consists of discrete packets, while the other applied this understanding to atomic behavior, illustrating that electrons operate within a structured system rather than chaos. Despite their own reservations about these ideas, they did not abandon them out of fear. Instead, they clung to them, believing they held a deeper truth, irrespective of their alignment with established beliefs. Their efforts yielded more than a scientific theory. They catalyzed a shift in humanity's approach to inquiry. Where science once focused on predictability, it began to embrace the realm of possibilities, a transformation that transcended laboratory boundaries, permeating our lives, thoughts, and relationships. Today, quantum theory operates within our phones, computers, medical devices, and communication systems, silently influencing our understanding of the world. It has illuminated the notion that certainty could be an illusion and that profound truths may reside within uncertainty. This theory has taught us to differentiate between observing and understanding. Often, things are not as they appear on the surface. Thus, we should delve deeper into any concept, person, or even life itself before passing judgment. The legacy of these two minds lies not merely in the equations they formulated but in the wisdom they imparted. If one remains tethered to old paradigms, new insights will remain elusive. Conversely, the courageous pursuit of inquiry can unlock the universe's mysteries. They did not create a singular path for everyone to follow. Instead, they opened a gateway for future generations to explore with curiosity, questions, and discoveries. This exemplifies the essence of science. It is an ever-evolving journey, where each answer spawns new questions, and the courage to question is the true legacy that transcends time.